Welcome back to the deep dive. We're here to break down complex stuff, cut through the noise, and give you the core insights. Today, we're tackling something really foundational in chemistry, but also, well, surprisingly elegant. The IUPAC Nomenclature rules. IUPAC, that's the International Union of Pure and Applied Chemistry. They're basically the ones who set the standards for the language of chemistry globally. We've been, digging into their guidelines, specifically how organic compounds get those unique, very precise names. It's the system underpinning chemical communication worldwide. Our mission today is really to give you a shortcut, help you make sense of those sometimes intimidating chemical names so you can actually see the molecule hiding inside the term.
Yeah, and it's fascinating, isn't it, why this system is just so vital. I mean, think about it. Imagine the chaos if every scientist, every lab just made up their own names for chemicals.
Or total confusion.
Exactly. It would be impossible to collaborate or even just to order supplies safely. This system, IUPAC, it provides a universal, completely unambiguous language. So when a chemist in Tokyo says methane and one in Paris says methane, they mean the exact same thing.
Right.
And that clarity is just critical. For research, yes, but also for safety, for industry, for everything.
That universal clarity is definitely the key takeaway there. Okay, so let's start at the beginning. The simplest building blocks. Saturated hydrocarbons, we usually just call them alkanes. These are the most basic organic compounds, right? Only single carbon bonds, kind of the backbone molecules.
Yeah, exactly. And that word saturated, it tells you something important.
Yeah?
It means every carbon atom is bonded to the maximum possible number of hydrogens it can hold, given its connections to other carbons. They're like full up with hydrogen.
Saturated, yeah.
And that saturation, well, it makes them pretty stable, generally less reactive than other types of hydrocarbons.
Which is why they're often fuels or solvents.
Precisely. They're not really looking to react or change easily. They're kind of chemically content as they are.
Okay, so we have these stable, single-bonded molecules. How do we actually start naming one? Like, if you see a structure, what's the very first step according to IUPAC? Let's say we want to name 2-methylpentane. Where does that name come from?
Right. Well, the first job, and it sounds simple, but you can get tripped up, is finding the longest continuous chain of carbon atoms.
Okay, the longest chain.
This is your parent chain.
Yeah.
It gives you the base name. So if your longest chain has 5 carbons, the base name is pentane. 6 carbons, hexane.
Ah, and that ending tells us it's an alkane.
That's your first big clue, yeah.
Yeah.
Ana means single bonds only, saturated.
I can see how you might miss the longest chain if it, bends around a corner.
Oh, absolutely. It has to be continuous, but it doesn't have to be straight on the page.
Okay, so we found our parent chain. Say it's 5 carbons, pentane. What's next? Because just pentane isn't enough if there are branches.
Right. The next critical step is numbering the carbons in that parent chain. And the rule is you start numbering from the end that's nearest to the first branch, or what we call a substituent.
Substituent, like a side group.
Exactly. Think of it like assigning house numbers on a street. You want the first house, the first substituent, to have the lowest possible number.
Makes sense.
Yeah.
What if you could start from either end and the first branch gets the same number? Like number 3 from both directions.
Ah, good question. That's the tiebreaker rule. If the first substituent gets the same number either way, you then look at the position of the second substituent. You choose the direction that gives the second one the lower number.
Okay, so it's a hierarchy. Lowest for the first, then lowest for the second, if needed.
Precisely. It ensures there's only one correct way to number any given chain.
Got it. So parent chain identified, chain numbered. Now we need to deal with those branches, the substituents. What are they usually?
Typically, they're smaller hydrocarbon groups themselves. We call them alkyl groups.
Alkyl groups.
Yeah. The most common one you'll see is just a single carbon hanging off, a Delancey's group. That's called a methyl group.
Methyl, like methane, but attached.
Exactly. Take the alkane name, drop the ane, add yol. So methane becomes methyl. Ethane, 2 carbons, becomes an ethyl group, CH yer. Propane, 3 carbons, becomes propyl, CH, and so on.
Okay, so 2-methylpentane literally tells you methyl group on the second carbon of a 5-carbon chain. It's like a little address.
It is a precise molecular address.
What if there's more than one of the same type of group, like 2 methyl groups?
Then we use prefixes, D for 2, tri for 3, tetra for 4, and so on.
Ah, okay.
So if you had 2 methyl groups both on the second carbon of a butane chain, you wouldn't write 2-methylbutane. It's clumsy.
Right.
You'd write 2-gila-2-dimethylbutane. You use a number for each group, separated by commas, and then the prefix di before methyl.
2-figure 2-dimethylbutane. Clear. Okay, now here's where it gets potentially confusing. What if you have different substituents, say, an ethyl group and a methyl group on the same chain? Which one do you name first?
The rule here is simple. Alphabetical order.
Alphabetical. Okay, so ethyl before methyl.
Exactly, because he comes before him. But here's the crucial part, and where people sometimes slip up. You ignore the prefixes ditri, tetra, when you're alphabetizing.
Oh, really? So dimethyl still gets alphabetized under M, not D.
Correct. You alphabetize based on the root name of the substituent methyl, ethyl, propyl.
Yeah.
So if you had a compound like 3-ethyl-2-methylhexane,
Okay.
ethyl's listed first because he comes before M, even though the methyl group is on carbon 2 and the ethyl group is on carbon 3.
That's a key detail. Ignore the multiplier prefix for alphabetizing.
You keep things consistent across the board.
And then there's the punctuation. Dashes and commas. They seem very specific.
They are, and for good reason. It's all about removing ambiguity. Numbers are separated from letters by a hyphen or a dash.
Like 2-methyl.
Right. And numbers are separated from other numbers by a comma.
Like 2,2-dimethyl.
Exactly. And the whole name is written as one word. No spaces, except possibly around things like cis or trans, which we'll get to.
Wow, so like 3-ethyl-2-dimethylhexane would be all run together like that?
All one word, with hyphens separating numbers from letters and commas separating numbers from numbers. It ensures that anyone, anywhere, reads that name and draws the exact same structure. No room for error.
It really is a precise language. Okay, let's maybe take an example from the source. 2,2-dimethylpropane. How does that break down?
Okay, propane tells us the parent chain is 3 carbons long.
Right.
Dimethyl tells us there are 2 methyl groups. And 2,2 tells us both of those methyl groups are attached to the second carbon atom of that 3-carbon chain.
The middle carbon.
The middle one, yeah. So you have a central carbon bonded to 2 other carbons and also to 2 methyl groups. So it's called neopentane. It's a common name.
Got it. The system works. Okay, so that covers the basics for alkenes, the saturated guys. Now, let's add some complexity. What happens when we introduce double or even triple bonds between carbons?
Now we enter the world of unsaturated hydrocarbons. Alkenes have at least one carbon-carbon double bond, and alkenes have at least one carbon-carbon triple bond.
Unsaturated, meaning they don't have the maximum possible hydrogens.
Exactly. Those multiple bonds take up bonding capacity that could otherwise hold hydrogens. And this isn't just a naming change. It fundamentally alters the molecule's behavior.
How so?
Well, those double and triple bonds are regions of high electron density. They're much more reactive than the single bonds in alkanes. They become sites where chemical reactions readily happen.
So they're more chemically active.
Definitely. It opens up a whole new range of chemical possibilities. Their shape changes too, especially around double bonds.
Okay, so more reactive, different shapes. How does the naming change to reflect this? Do we still find the longest chain?
This is the first big shift. For alkenes and alkenes, the parent chain must contain the multiple bond. Even if there's a longer carbon chain elsewhere in the molecule, if it doesn't include the double or triple bond, it can't be the parent chain.
Priority goes to the multiple bond for choosing the chain.
Absolutely. And the ending of the parent name changes too. For alkenes, it ends in N. For alkenes, it ends in an.
So a 3-carbon chain with a double bond is...
Butene.
And with a triple bond.
Propene.
Okay. And how about numbering the chain? Does the multiple bond get priority there too?
Yes, it does. You number the parent chain, starting from the end that gives the multiple bond the lowest possible number.
Yeah.
This takes priority over giving substituents low numbers.
Lowest number for the double or triple bond itself.
Right. And you indicate its position using the number of the first carbon involved in that multiple bond.
So if you have CH hero,
Yeah.
that's 4 carbons, a double bond starting at carbon 1.
That would be but one man.
But 1 air, okay.
Yeah.
And if the double bond was between carbon 2 and 3?
That would be but 2 ene.
Got it. The number tells you where the ane or ane starts. What if you have both substituents and a multiple bond?
The multiple bond still gets priority for the lowest number when deciding which end to start numbering from. After you fix the numbering based on the multiple bond, then you just list the substituents with their numbers and names alphabetically, just like we did for alkenes.
So the substituent rules kind of layer on top.
Pretty much, yeah. Identify the parent chain with a multiple bond, number it to give the bond the lowest number, locate the bond with its number, then name and number the substituents alphabetically.
What if? What if a molecule has more than one double bond or triple bond?
Good point. Just like with substituents, we use prefixes. 2 double bonds is a diene, 3 is a trane, 2 triple bonds is a dene.
Right.
And you need a number to locate each one. For example, CHH, CHH. That's 4 carbons with double bonds starting at 1 and 3.
So butadiene.
Almost. We actually
Okay.
add an A back to the stem name for pronunciation, so it
Mhm.
becomes Buddha 1-cal-3-10 Ane.
But ne-1,3-dienene. Got it. Easier to say.
Yeah. Same for things like octa-1,3-2-methyl-5-terane.
Okay, that makes sense. Now, you mentioned shape changing with double bonds. There's something special about alkenes here, isn't there? The cis-trans thing?
Yes. This is really interesting because you can't freely rotate around a carbon-carbon double bond like you can around a single bond. The groups attached to the double bonded carbons are fixed relative to each other.
Fixed in space.
Fixed in space. So if you have different groups attached, you can have different spatial arrangements called stereoisomers. The simplest type for alkenes is cis-trans isomerism.
Cis-trans. I've heard of that. What does it mean?
Okay, look at the 2 carbons of the double bond. If you have, say, similar groups attached, cis means they're on the same side of the double bond. Trans means they are on opposite sides.
Same side versus opposite sides.
Exactly. And this isn't just a technicality. Cis and trans isomers are different molecules with different shapes and often very different physical and biological properties.
Wow. So same formula, same connections, but different 3D arrangement makes it a different substance.
Absolutely. Think about trans fats versus cis fats in food. They have the same basic fatty acid structure, but that one geometric difference around a double bond drastically changes how our bodies process them.
That's a huge difference from such a small chain.
It is. Or, in vision, the molecule retinal flips between a cis and a trans form when light hits it. That tiny shape change is the first step in seeing. So this geometry is incredibly important.
So how do we indicate cis or trans in the name?
You just put cis or trans in italics out front, followed by a hyphen, like cis but 2 or trans but 2.
Okay. What if the groups attached are all different? Can you still use cis-trans?
It gets ambiguous then. For more complex cases or when you don't have 2 identical groups to compare, we use a more general system called the EZ system. Yeah. It uses rules based on atomic number to assign priorities to the groups on each carbon of the double bond. Then it compares the higher priority groups. If they're on the same side, it's Z from German zusammen, together. If they're on opposite sides, it's E from entgegen, opposite.
So ISI is like a more rigorous version of cis-trans.
Essentially, yes.
Yeah.
It provides an unambiguous way to describe the geometry around any double bond that can have stereoisomers.
Fascinating. The level of detail is amazing. So let's just quickly recap the comparison.
Sure.
We have alkanes, saturated, all single bonds, stable, parent name ends in E's, like propane.
Right, your basic scaffold.
Then alkenes, unsaturated, at least one double bond, more reactive, geometry matters, cis-trans, or easy. Parent name ends in E, like prop 1 or trans but 2Z.
Yeah, the double bond is the key feature.
And alkenes, unsaturated, at least one triple bond, generally very reactive, linear geometry around the triple bond. Parent name ends in E, like ethane, which is also called acetylene.
Exactly. Each suffix, ane, tells you immediately about the fundamental bonding and reactivity you should expect.
It really is a logical system. It seems complex at first, but it's built layer by layer on these core principles. Find the main chain, number it right, add the substituents, note the bonds, consider the geometry.
That's the beauty of it. It creates order from potential chaos, a universal language built on logic.
Well, that brings us near the end of this particular deep dive. We've journeyed through the systematic world of IUPAC nomenclature, starting with those simple alkanes and moving through the double and triple bonds of alkenes and alkenes, even touching on their 3D shapes.
And hopefully you now have a much better feel for this critical language chemists use everywhere. It's not just about memorizing rules. It's about understanding how a name encodes precise structural information. It should empower you to look at those long chemical names and, well, not be intimidated, but actually see them as blueprints.
Absolutely. So here's a final thought to leave you with. Next time you see a chemical name, maybe on a product label or an article, pause for a second. Don't just skim it. Could you, maybe, just from the name, sketch out the basic carbon skeleton? Could you picture 3-ethyl 2,2-dimethylhexene? Or even think about why trans but 2-in might behave differently in a reaction compared to its cis twin, just because of how things are arranged in space. The name holds the key. Thanks for joining us today on The Deep Dive. Until